Diffusion is one of the physical principles we need to understand if we're going to understand how biological systems work. And diffusion, in essence, is very simple. Diffusion occurs in fluids, that is liquids and gases, and when they are brought into contact, they will mix up with each other until their concentrations are equal throughout. So diffusion is simply the physical process whereby liquids and gases mix up with each other when brought into contact until their concentrations are equal throughout. So let's think of a really simple example of diffusion now. Let's think about putting some ink into a beaker full of water. So if we think about a beaker full of water, here we have a beaker or a glass or whatever it happens to be. And this is full of water. And as you know, water is molecules. Water is H2O. So actually what we have in here is lots of individual water molecules. Now you might know that there's such a thing as absolute zero, the lowest possible temperature you can ever get. And that is minus 273 degrees centigrade. But why is there an absolute zero? Why is it that things can be cooled down to minus 273 degrees centigrade and can never go any colder than that? Well, the answer is in what is called kinetic theory. So heat is movement, kainos is Greek for movement, kinetic theory. All particles, all substances which possess temperature, that temperature is determined by how quickly the individual particles that make up that material are vibrating. So if you heat something up, what you're actually doing is increasing the kinetic energy of the molecule in the substance, of the molecules in the substance that those molecules make up. So if something's cold, the molecule might be vibrating slowly. Then if it heats up, the molecule vibrates more quickly and more quickly and more quickly. And in theory, if you put more and more energy into something, it can get hotter and hotter and hotter. So inside stars, you have the most preposterously high temperatures. But then when you cool something down, the molecules vibrate slower, and they vibrate slower, until eventually the molecule will stop. And when it stops, that temperature is equal to minus 273 degrees centigrade. Molecules cannot get slower than standing still. Molecules or atoms cannot get slower than standing still. So the point is that fluids at biological temperatures, certainly, made up of individual, in this case molecules of water, by virtue of the temperature of that water, there's going to be vibration in the molecules. And of course, the hotter the water, the greater the vibrations are going to be. So if we just take water at a biological temperature at 37 degrees centigrade, each water molecule is not keeping still. It's actually vibrating back and forward. And it's vibrating back and forward in a random way. There is molecular vibration. That is what the kinetic theory is. So when you take a beaker of water, the water molecules are not still, they're all actually in motion. The water might look still to you looking at it, but on a molecular scale, you can see the molecules are actually vibrating. And then we come along and introduce some ink. Let's have a different colour. So here's some ink in here. So now we've introduced a couple of ink molecules. In fact, we'll introduce a few ink molecules. So we've now introduced some ink molecules. These are red ink. And assuming they're at the same density as the water molecules, so they don't settle out, then what's going to happen is that the ink molecules are going to be vibrating, but of course the water molecules vibrate, so inevitably they're going to bump into each other. And there's going to be untold billions of random collisions between the ink molecules and between the water molecules. They're all going to vibrate. And because these vibrations and these collisions are going to be random, eventually there's going to be random distribution of the ink molecules through the medium of the water. And that will actually go on, because there's so many billions of collisions, that will go on until the concentration of the ink molecules becomes equal throughout the solution. So instead of having a clear water bit and a red inky bit, we'll end up with a pinkish bit all over, because the ink molecules will diffuse throughout the available medium. So in this context, the ink molecules are solute molecules dissolved in the water, which is going to be the solvent. And this is important in quite a lot of biological processes. So for example, let's consider the alveoli in the lungs. The air sacs in the lungs, and these are very enfolded to give a large surface area. And then over the surface of these, there's going to be many blood capillaries from pulmonary capillaries. This diagram just shows 2 capillaries. In practice, the alveoli are essentially completely surrounded with blood capillaries in the same way that my fingers are surrounding my hand, even more so. Imagine I had 10 fingers. The capillaries completely surround the alveoli. Because what happens is, when you breathe in, you're going to increase the amount of oxygen in the air in the alveoli. But because the blood going through the pulmonary capillaries has come back from the systemic circulation, it's been pumped out from the right side of the heart into the pulmonary arterial system, the blood arriving here is relatively low in oxygen. So we have a situation where there's a relatively high amount of oxygen in the alveoli, but a relatively low amount of oxygen in the blood. So diffusion is going to take place from areas of high concentration to areas of low concentration until the concentration is equal throughout. So what this means is the oxygen will diffuse into the blood, passing through the pulmonary capillaries. And what's actually happening here is, if we think about the pulmonary capillary here, so if you think about the alveoli there, imagine that's the alveoli, and imagine that this is the pulmonary capillary. We've said that there's more oxygen in the alveoli and relatively less oxygen in the pulmonary capillary. In other words, there's a gradient. There's more oxygen there than there is there. So what will happen is the oxygen will diffuse down what is called its diffusion gradient. So because there's more oxygen in the alveoli than there is in the blood, the oxygen will diffuse down its diffusion gradient. Because diffusion will always take place from areas of high concentration to areas of low concentration until the concentrations are equal throughout. And conversely, the blood arriving in the pulmonary circulation is going to be relatively high in carbon dioxide. But the fresh air, or relatively fresh air, or the air that's been refreshed from the outside atmosphere in the alveoli, that's going to be relatively low in carbon dioxide. So we have a situation here where the blood is relatively high in carbon dioxide, but the air is relatively low in carbon dioxide. Therefore, the carbon dioxide is going to diffuse from areas of high concentration to areas of relatively lower concentration. So it will diffuse in that direction from the blood into the air in the alveoli, and that will then be breathed out. So in this situation, the diffusion gradient is going to be highest in the blood, and the carbon dioxide will diffuse down its diffusion gradient from the blood into the alveoli, down its diffusion gradient. So the oxygen is diffusing down a diffusion gradient from the alveoli to the blood, and the carbon dioxide is diffusing down its diffusion gradient from the blood into the alveoli where it can be exhaled. But of course, because the blood is constantly circulating, equilibrium is not reached, and this process is ongoing. So oxygen is constantly diffusing from the alveoli into the blood. Carbon dioxide is constantly diffusing from the blood into the alveoli. And of course that is necessary, because if that did not happen, we would not be able to oxygenate the blood, and of course life would not be able to continue. Now, as you learn more about human biology, you'll come across lots of other instances of diffusion. Sometimes the diffusion takes place through a membrane, other times it doesn't, but very often in biology it takes place through a membrane. And of course this membrane, or these membranes in this case, here we have the capillary endothelial membrane and the alveolar membrane, both of those need to be permeable, in this case to the oxygen and to the carbon dioxide. But you'll come across many examples of this. For example, you might come across the absorption of nutrients. And again, that's facilitated by a very large surface area in the small intestine, with circular folds, with villi, with microvilli. In fact, people have estimated that there's up to 400 square meters of internal surface area in the small intestine to facilitate the diffusional absorption of nutrients from the gut into the blood. And the situation is actually the same in the lungs. People have estimated that in a healthy lung, there's 70 square meters of internal alveolar membrane to facilitate this vital, ongoing process of diffusion. So a fairly simple physical process, but absolutely essential to numerous life-giving biological functions.